For this example, we're looking at more complicated linear transformations. And because we're looking at more complicated linear transformations, we really have to leverage this coordinates basis in order to use the technique that we've developed. And we're able to pick the coordinates now. So we're going to go back to nice bases. But we can see that because we're using the polynomials in this example, those nice bases, we still want to represent in our coordinates vector and then just convert when we're done. First thing we're going to do is we're going to actually show that this transformation is a linear transformation. And to show it's a linear transformation, we're going to let g of x and f of x be in P2R and C1, C or C and D be in the set of real numbers because our field is real in this example. We're going to consider T of A f of x plus B, or I guess it's C and D, so C f of x plus nope, that's not working, plus D g of x. And this is going to equal, and this is my left side, this is going to equal C f of 1 plus D g of 1, comma, C f2 plus D g2. And my right side is going to be A T f1 or fx plus B T of gx. And this equals to bracket A times f1 f2 plus, or not A, should be C, B, C. This is going to be C f1 f2 plus D g1 g2, which is equal to CF1 CF2 plus DG1 plus comma DG2. Adding these two together, we get CF1 plus DG1 plus C, or comma, CF2 plus DG2. And we see that the right-hand side, the left-hand side, the left side equals the right side. Therefore, T is, in fact, a linear transformation. And in this process, going backwards might be challenging. Taking T and going the reverse direction for our linear transformation might be challenging, but going in the forward direction, it's fine. And we can just manipulate and rearrange, and we get our results. Next thing we're going to do is we're going to compute what T of the matrix representation of T using bases alpha beta of our linear transformation. So we're going to look at, first we're going to compute what T does to 1, and I'm going to convert to red. We're going to look at what T does to 1, T does to x, and T does to x squared. And T of 1 is P of 1, P of 2, which 1 is just 1. And this equals 1e1 plus 1e2. Looking at what T does to x, this gives us 1, 2, which equals 1e1 plus 2e2. And looking at what T does to x squared gives us 1, 4, which is 1e1 plus 4e2, giving us the matrix representation alpha beta of our linear transformation being 1, 1, 1, 2, 1, 4. From here, we'd like to compute the kernel. And to compute the kernel, what we're going to do is we're going to solve the homogeneous system 1, 1, 1, 2, 1, 4, equaling the 0 vector. And our solution vectors represent our kernel using the coordinates alpha, or using the coordinate vectors that are created with the basis alpha. So first we're going to do is we're going to take row 2 minus row 1, replacing row 2, to solve and convert this matrix into echelon form. On 1, 1, 0, 0, 1, 3, 0, and now row 1 minus row 2, replacing row 1, gives us 1, 0, minus 2, 0, 0, 1, 3, 0, giving us the equivalent system of equations. A minus 2c equaling 0, and b plus 3c. Now we're going to let v be in the solution space. Then v equals a, b, c. Now here, what are my free variables and my basic variables? Well, my free variables and my basic variables. My free variables is the variable c. My basic variable is a, p. Now, letting c equal t, which is an element of the real numbers, this gives us that a equals 2t and b equals minus 3t. This means that v equals 2t minus 3t t, where t is an element of the real numbers, or v equals t times 2 minus 3, 1. Okay, so the span for my solution space, the solution space equals the span of the set of vectors 2 minus 3, 1. Now, I want to convert this into the kernel. And to convert it into the kernel, what I'm going to do is I'm going to take each of these vectors and figure out what they are using the basis alpha. Well, I'm going to move this down. And right now I have v alpha equals 2 minus 3, 1. What does this imply? This implies that v equals 2 times the vector 1 plus negative 3 times the vector x plus 1 times x squared. So v equals 2 minus 3x plus x squared. So my kernel of t equals the span of the vector x squared minus 3x plus 2. And now we can kind of see how this process is so powerful, because all I have to do is follow the exact same process I was doing before, and I'm only converting whatever these vectors are in the span of my solution space to the corresponding vectors in W using the basis alpha. We get a similar process for computing the image. And for the image, we're looking at the span of the columns in our matrix. So we want the span of these vectors. And here what we're going to do is we're just going to take the vectors corresponding to the basis variables. So the column space for T alpha beta equals the span, and we only take those column vectors corresponding to the basic variables, which if we scroll up, those column vectors are 1, 1, and 1, 2. Now we're going to represent each of these vectors corresponds to a vector in the image. So if V beta equals 1, 1, this implies that V equals 1 times E1 plus 1 E2, which equals the vector 1, 1. And if V in beta equals the vector 1, 2, this implies that V equals 1 E1 plus 2 E2, or equals to 1, 2. Well, this gives me that the image of T equals the span of the set 1, 1, 1, 2. Well, I can use these to create my bases. So my basis for the kernel T equals the set x squared minus 3x plus 2. And the basis for the image of T equals the set 1, 1, 1, 2. Our process is extremely similar to what we did before. The only difference is converting our solution space and our column space, or the spanning sets for our solution space and our column space, into bases for the image of T and the kernel of T by using the bases